All right, guys. So here is a question I think I left at last Monday. What can happen here? A teacher working in Children Are My Sunshine inner city school, but the 101st pupil in that school is Dennis the Menace. After a long work day, the teacher sits to rest in her favorite chair, only to discover much too late that it is littered with board pins. Furious, the teacher goes at once to see the principal and demands that Dennis be immediately expelled. She is armed with the following indisputable evidence. Okay? And this evidence is, first, it is known that one of the 101 pupils must have perpetrated this particular crime. Exactly one person, it's known. Okay? If Dennis were innocent, then the probability of such prank would be 0.001 that it will occur. So it is this school's policy to regard the pupil guilty of a misdemeanor if the probability of innocence is between 0.05, is below, sorry, 0.05. What should the principal do? Do you understand the question, guys? So there is this wonderful inner city school, and there is Dennis the Menace is going to that school. He's the 101st pupil. The question is this: so there were board pins laid on this teacher's chair, and it's known that exactly one person, for whichever reason, it's known. Maybe the person, there is a camera recording, and you can look at it. One person entered, maybe masked, and placed the pins, and it's obvious that this person was one of the pupils because maybe there is a tag that you cannot enter the school otherwise, right? So those are this is the information that's known. And if Dennis were innocent, given that Dennis is innocent, the probability of the prank is 0.001, 1 out of 1,000 that this thing will occur if Dennis is innocent, is not involved. Okay. The question is, what should be done to Dennis? Should it be blamed for this misdemeanor or not? Do you understand? Interesting question, yes. So makes sense what I'm asking. Given that Dennis is innocent, this event would have been very rare. It's not a common event, 1 out of 1,000 that it will occur. It says my internet connection is poor. Can you, or unstable? Do you, you're still receiving signals from me, yes? Wonderful. By the way, as I mentioned, your exam is graded. I haven't yet sent you the messages because I don't want to make you too sad before the lecture, right? It's okay though. Don't be scared about that exam. It's a hard exam. We will see how well you do with the second exam. And of course, by the way, some people I think tried so hard. They did get a good score, but I'm very convinced that it's not theirs. Am I being that teacher?
So Professor, for this question, so the output would have to be less than 0.005 in order to think that Dennis is innocent, right?
It's basically if the probability of innocence given the crime of Dennis is below 0.005, then we are going to convict him of the crime. In other words, he's going to be, the parents are going to be called, maybe there is going to be expulsion or suspension. You understand? Something will happen.
Oh, the probability of innocence is below 0.0. Okay, so if the probability of innocence is that low, okay.
Yes, if the probability of innocence is low, and this is what's known. Because, I mean, this teacher has taught classes without Dennis the Menace, and pins occurred in maybe 1 day out of 1,000, you know? So on average, on 1 out of 1,000 days, this teacher sits on needles, right? So it happened before when Dennis was not involved. So the question is, what should be done based on this evidence? Do you convict or do you not convict? All right, as we have little time, I mean, I'm going to give you just 1 more minute, 2 more minutes maximum, and then I have to move. Speaking of which, do you have time on Monday? I mean, you know, Monday is already, the semester is over, but we have much material to continue to cover, and I intend to just go on, right? So if you want to show up, if not, we'll just have to decide if it's a good day for you to show up, right? So the lectures here I have also for chapter 6. I want to cover this for whatever. I mean, I'm assuming you're learning probability for some particular purpose. I would like you to be strong in the subject, right? So I would like to finish the full program, even though we're behind. All right, so do you understand the problem we're dealing with? Yes, guys? And let's, I suppose, then solve it together, see what can be said about this particular situation. So one student is known, out of 101 students, one student is known to have committed a crime, one of them for sure. Now, the teacher believes it's Dennis because such an event will be very unlikely if Dennis were not involved, right? If it were Dennis were not involved, it happens maybe once in every 1,000 days. Good. So the question is it Dennis or is it not Dennis? So here is the argument that we can look at it. So the principal looks into his directory on juvenile delinquents and finds that out of 9,001 young sociopaths, on the average, only one will place board pins as a prank. There is a recording of whatever they did there. It is also estimated that a good pupil is likely to commit this prank with probability 10 to the power of -5. So a good student might also kind of have his day and do something like that. So let I be the event that Dennis is innocent and E be the event this crime is committed. Okay? So probability that Dennis is innocent is that you know, it's based on that book, right? Is that he's one of the juvenile delinquents in the school. It's that basically it's that 9,000 over 9,001 in general that you know that such a thing would happen. So the probability of evidence given that he is innocent is not very likely. So that would be 10 to the -3. Good. And the probability of evidence given that he is not innocent, it's 1. So if he's not innocent, that means he did this crime, and of course that evidence will happen. Good. So then what we'd roughly do is this. So this is basically the estimation of some sort of suppose estimation of how likely Dennis is to be innocent in general, right? Without any information, how likely is he to do something? Okay, so what you have is the probability of I given E is the probability of just reverse it, E given I times probability of I divided by probability of E given I times probability I plus probability E given I complement probability I complement. Good. So that would be what? That would be a probability of evidence given that he is innocent is unlikely. It's 10 to the minus 3. Probability of his innocence to begin with is, let's say, fairly high without anything happening there, right? So, probability that he is not gonna do anything is fairly high. That's an estimation of how likely a juvenile delinquent to do a particular act. Understand? A very particular act. So that's how that's kind of how we estimate based on the books, because we observed a bunch of juvenile delinquents. We have a bunch of them on the record, and it said that we have an estimate on how often does one of them commit the crime. So look what happens here. So we have this number. When we simplify it, the probability that he is innocent given the evidence actually ends up being very high. It ends up being 90%. Based on this information, you see, even though, so you see the mistake here is to assume that the evidence, given that he is innocent, the evidence would have been not likely, right? But what we want to understand is the evidence, the situation, the crime has happened. What's the probability that he is innocent? The confusion that you might have drawn here is there is a difference between probability that you are innocent given that you have this crime committed evidence, and the probability that the crime is committed given that the person is innocent. You understand? So those are not the same thing. That's called prosecutor fallacy. And there was an actual case like that. Here is the actual case that happened here. So in 1998, Sally Clark was tried for the murder of 2 of her sons because they died shortly after birth, each of them. During the trial, an expert witness for the prosecution testified that the probability of a newborn dying of sudden infant death syndrome was 1 out of 8,500. So the probability of 2 deaths due to SIDS is in one family, according to this witness, was 1 over 8,500 squared, or about 1 in 73 million. So you see, basically his or her, not hers, who was this expert witness, claimed that it's very unlikely that 1 child dies, and it's very unlikely that 2 children will die therefore, right? And so the evidence is, it claimed, it's 1 in 73 million, right? If the person is innocent. So the assumption, if innocence makes it kind of makes some sort of event very unlikely. So the conclusion was that she was guilty and she was sent to prison, right? As it happened, so as it happened, of course, you can think of 2 important errors that happened here. One error is what is that 1 out of 8,500? It's that let's see. That's the probability of a randomly selected newborn dying of this disease. You see. Right, so you look at out of what? So I suppose it must be a bit more precise. So you look at the situation. You look at newborns that died unexpectedly, right? And you see that the ratio of those newborns that died unexpectedly to total newborns is 1 out of 8,500. Why do we square it? I mean, it's not like the second child was again randomly selected. The second child, you see, if there is some genetic deformity, the fact that one child died might make her genes or some genes that are transmitted to this child particularly bad for newborns. You see, so it's the second child was not randomly selected. Make sense? So this number to begin with is not correct. It's not correct without any further justification to say 1 over 8,500 squared, because you're not picking independently the next child. The next child is picked of the same mother, right? This is only if you take one random child and then another random child. The probability that both will be dead from seeds is very low. But not if you pick one child and from the same mother another child. So that's one thing about the evidence. So what can we say here? So the death of the two children isn't necessarily independent if it is caused by SIDS, by sudden. I'm not sure what sudden death syndrome is, but they are not necessarily independent. So death of one sibling might make the death of the other very likely, perhaps. Right? So maybe it's more so in the order of 1 out of 8,500 rather than squaring the number. The expert witness speaks about the likelihood also of the evidence under the assumption of innocence. So the evidence given innocence is the probability calculated, but what we need to calculate is the probability of innocence given this evidence, which is, well, just condition. It's probability of evidence given person is innocent times probability of innocence. And the probability of innocence, initial innocence, might be very high. It's very unlikely that a mother kills her own children, right? So so maybe this number, probability of evidence given, probability that evidence will happen given the person is innocent, it could be a very low number, but the probability of innocence will be very high. So together they cancel each other to be perhaps maybe the probability here will be high. So you see what I'm saying, right, guys? So so this is maybe like close to 1, and this is evidence given the person that the person is innocent. Is not innocent. This might be a small number. This might be yeah, so the ratio, basically this ratio might be close to 1. That's what I'm trying to say. You understand what I'm saying, guys? Because it's not also not the same things. A probability of evidence given the person is innocent is very different than the probability of innocence given that the evidence has occurred, the situation has happened. Okay, so there are more questions for applying the normal distribution. Let's walk and see what else is there. So the next distribution is the beta distribution. That's a pretty interesting distribution. Okay, so the beta distribution is a continuous distribution on the interval from 0 to 1, and it is the generalization of the uniform random variable. Okay, so it's one of the first natural generalizations of the uniform random variable. So we say that a random variable x has the beta distribution with parameters a and b, where both parameters are bigger than 0, if the density function is of the form x to the a minus 1 times 1 minus x to the b minus 1 divided, this is just a number that is normalizing this distribution, because the integral must equal to 1, right? This constant is just a constant that is equal to the integral from 0 to 1 of x to the a minus 1, 1 minus x to the b minus 1. Good? I will explain why that distribution is useful in a moment. So if I select 1 and 1 for beta, right, so it will be 1 minus 1 and 1 minus 1. So beta 1, 1 is just the uniform distribution over 0, 1. Okay? And in general, the distribution has the following shapes. If a and b are smaller than 1, then it happens that the distribution is U-shaped. Okay? if both A and B are bigger than 1, the distribution is frowning down. It opens down. And if A is equal to B, the distribution will be symmetric about 1/2. If A is bigger than B, then the numbers closer to 0 are favored to numbers closer to 1. Okay, like this. So A smaller than B. The smaller the A, the more yes, the more the favor is towards how should I say
positively skewed, right?
Huh?
Is it positively skewed?
Yes,
right?
it's positively skewed, exactly. Right. So you will see what's the idea, right? So this is supposed to, you'll see with an example. And here, if A is bigger than B, we have all sorts of shapes, right? We have this shape, and then here we have if B is equal to 1 and A is bigger than B, it will be something like a straight line. Okay, so we will understand what this distribution is about in the special case where A and B are positive integers. Okay, and there is a good example of how that is supposed to work. Okay, so let me perhaps, before I continue, just give you a sort of heads up of what this is about. So generally, imagine that you're trying to simulate a certain event. You're trying to understand how prevalent something or how likely something to happen. Okay, you don't have that probability. So you're trying to estimate the probability. Okay, I will show you with. So for example. For example, this is the situation, right? So let's say you have an election, right? And you have an election, and let's say 65% of the votes for the election are in, and let's say there is so many of them are for candidate X, and some others are for candidate Y. How likely, given this information, that candidate X will win? If, of course, the sampling is done randomly. You understand? So this beta distribution will give you an estimate of the probability. So it will give you a range of probabilities between something and something, right? So it will tell you that candidate X is likely to win between, let's say, more or less 0.3 to 0.7, or from 0.8 to 0.10 or something, right? Probability of victory. It gives you a range of estimates, and you will see down below how that's supposed to work. You just think about tossing coins, right? Not necessarily fair coins, right? So let's say you tossed a coin 50 times, and 30 of those tosses came out to be heads. And then you estimate what's the probability that when each time you toss the coin, you get heads. Okay, that's kind of how it's gonna work. Make sense? So I'll show you in a moment how that will be. So first, I have this proposition. So so the integral from 0 to 1 of n choose k, x to the k, 1 minus x, n minus k, this integral is equal to 1 over n plus 1. Okay, and I'm going to show you why. So here is the proof. Okay, so here is the interval, right? And what you do is you randomly pick n plus 1 points on the unit interval over 0, 1, and color n of those points black, and 1 point you will color red. That's going to be the special point. Okay, like over here, P, right? And then you are going to define the random variable x to equal 0, 1, all the way to n. Okay, to be the number of those points or atoms before the red point. Okay, how many do I get below the red point? You understand? They are randomly distributed over the interval 0, 1, and one of them is colored red, and I want to know the probability that a certain number is going to be below P. Okay, so let's see what sort of distribution we have here. So observe that the probability that I get k balls in here given that red is in location P, is going to be simply x equal to k, given that the red is in location P. Okay, and you see what happens here. So when I distribute those points, each is equally likely to go anywhere on the interval. Anywhere on the interval. Good. So you take point number 1, right? It's equally likely to go anywhere on the interval. What's the so if it's equally likely, it means we're using uniform random variable. You see that? So if you look at point number 1, you know, P is the n+1 point, right? It's equally likely to land anywhere on this interval. And what's the probability it lands below P? The probability is the length of this interval divided by the length of 1, or in other words, simply the length of the interval. You agree? The probability that ball number 1 lands below the point P is simply P, and the probability it lands above is 1 minus P. Do you get this point, guys? Please confirm if you understand what I said. And if not, please ask me questions. Good? You sure you understand? Yes, guys? So if I randomly distribute those points, if in other words, what do I mean by randomly? So there is each ball is equally likely to go anywhere on the interval, which means its distribution, or its you know, probability function is the uniform random variable. Agreed? Equally likely means you just imagine selecting, dividing this number line into tiny sectors. Each sector has the same probability, so we clearly see that the skyline is a constant, it's 1. So it's uniformly distributed for each of those balls, right? So what I'm saying is that given that the n+1 ball landed at point P, assuming that happened, right? Then the probability that ball numbered 1 lands below the point P is P, and above it's 1 minus P. Good? And the same is true about every other ball, because each of them independently is placed anywhere on the number line. So you see that? So the probability that x equal to k, given that red is at P, is simply n choose k, because that means that k of the balls are in this region. So which of the k? Which of those? It's n choose k, p to the k, 1 minus p to the n minus k. It's binomial. Yes? You see why it's binomial, of course, right? It's binomial because, well, each ball is independently landing anywhere on the interval from the other. So we have k successes. K of the balls landed below p. Which of those balls? N choose k, right? So we have a binomial distribution. Good? Now, what we have here is, you know, because the red point can land anywhere, right? So how do I figure out, you know, without knowledge where the red point landed, how likely are k to be below p? So this can be done by Bayesian statistics, right? By conditioning. And you can imagine doing the conditioning by making the situation discrete. Are you with me, guys? By making it discrete. So imagine that the n+1 point can land in discrete intervals. Okay, so that's what I try to explain here. So you partition the number line into, maybe I'll draw you another picture so it will help you. So I draw the interval 0 and 1, and I divide it into n sectors. I'll divide it into m sectors. So this is all the way to this sector, right? So the length of the sector, let's consider this length as delta x, m equal to 1 over m. Yes? Agreed? So m sectors. So then let's see how many possibilities are there for my special red ball to land, right? If it's divided into m sectors, it's equally likely to go into any of those sectors. So I can say that probability that red is in the interval, let's say from xk, or let's call it xj, to xj plus 1, right? The probability that it's over there is simply the same as 1 over m. You agree? Because it's equally likely to go in each interval. So it's 1 over m. Good. And so what I can see, and what is xj? Xj, you can think of it in terms of Riemann sums as the point j multiplied by 1 over m. That's the point xj. Are you following me, guys? So what you have here is I can condition, right? What the probability that x equal to k, in other words, that k of the balls land before the red ball, that can be thought of as the summation. I'm using Bayes formula, the summation, the summation j equal to 1 all the way to j equal to m. The probability of x equal to k, given that r is equal to xj. Yes? xj times the probability of r being equal to xj. And r, of course, is discrete. When I say r equal to xj, I'm discretizing it. I imagine that the previous interval, if it lands, for example, if it lands anywhere in here, let's say this is xj minus 1 and this is xj, I pretend that it lands at this point. You understand? I narrow it down and say it happened at the point xj. Good? So what do I get? I get here simply binomial, right? R equal to xj means what? Means r is equal to j times 1 over m. So I have here summation j equal to 1 all the way to m. And the probability that x equal to k given this particular j is it's n choose k times we have here j times 1 over m to the power of k, and then here we have 1 minus j over m to the power of n minus k, yes, times the probability that x equal to xj, it's just times 1 over m. And do you recognize this? If you did calc 1, this is a Riemann sum. This is a Riemann sum. Do you agree? This is the delta x, and this is j times delta x. J goes from 1 to m. It's the right-hand rule for the Riemann sum. Are you with me? So that means that if I continue taking this discretization, I will get the integral from 0 to 1, n choose k. I can think of it as x to the power of k, because j over m becomes x to the k, 1 minus x to the n minus k times dx. That's the 1 over m becomes the dx. So guys, I hope I'm not confusing anyone here. You all remember Riemann sums, or do you need me to say a few things about it? You remember how Riemann sums are set up? So by the process of discretization, I can very quickly see that it becomes an integral. Do you see that? So in other words, I'm claiming that the probability that x equal to k is equal to the above thing. If you have any questions, if I can assist you with something, please let me know. You all remember Riemann sums, and it's not just kind of nodding, so I leave you alone, right? I'm happy to explain. I want you to see how those formulas are produced. You see, so continuous probability is essentially nothing more than the discrete case, just but applied many times, right? You just if you make a very fine discrete case, it really is a good approximation to the continuous case, and so I can convert it to the situation. Yes. So and then I can calculate the probability that x equals to k much simpler. Right? How can I do it much simpler? It's because the n+1 ball is equally likely to be anywhere, right? So it's equally likely to be, on the other hand, the n+1 ball is equally, so if I have the whatever balls, how should I say, whatever balls we have the 1, 2, 3, right? All the way to n, and then the special ball, it's n+1. They are equally likely to have any ordering relative to each other, right? There is no preference to the sequence orderings, correct? So in how many of those orderings do we have exactly k balls to the left of the special red ball? Well, think about it. So exactly k, it means what? It means that once I arrange, I take the arrangement n plus. Sorry, just 1 second. So exactly k in between. It means that I can arrange the n factorial. Right? I have n factorial arrangements of the other remaining balls. And then afterwards place in the k position, in the k+1 position, place the red ball. And total arrangements are n+1 factorial, which gives me 1 over n+1. Do you follow? You see, guys. So I just do this Kafka protocol for the numerator. If it happened that the n+1 red ball is the k+1 ball, right? It's in the k+1 position. That means exactly k are below it. It means I can arrange, I can group all the others, and once I group the n objects, the position of the n+1 object is determined for this to happen. It must be the k+1 position. Yes. And total orderings is n+1 factorial. So what did I just observe? I just observed that we have that the integral is equal to 1 over n+1. Good. And in particular, this means that the integral from 0 to 1, it can be written in terms of a and b. Right, because I have here a minus 1 and b minus 1, so I can just I know how to solve this integral, right? So where the powers add up to n. So if I have a and b, if I have x to the a minus 1, 1 minus x to the b minus 1, I can take the sum of those values. It's a minus 1 plus b minus 1, or a plus b minus 2. Choose a minus 1. This number is equal to 1 over a plus b minus 1. Do you follow? Because it's this number n plus 1. Are you with me? And so that means that I can explicitly calculate the beta coefficient, which is the integral from 0 to 1 of x to the a minus 1 times 1 minus x to the b minus 1. All I have to do is I just have to divide everything by this a plus b minus 2, choose a minus 1. And when I rearrange terms, it looks like this. All right, so we will return to this beta in a moment. First, let's again look at how that's supposed to work. the beta distribution is very useful tool in predicting the likelihood of an event from data gathered through experiments. Yes? So let's consider this very basic experiment. We have a coin that lands heads with unknown probability P. Our goal is to infer the value of this probability P after observing the outcomes of n tosses of the coin. The larger n is, the more accurately we should be able to infer or estimate the probability. Do you agree? So imagine the coin is completely unknown to us. We have no preference, no idea what sort of outcome it will have. So what is the default distribution you should have for the probability of the coin P? Where is it likely to fall? Sorry?
Probability of like the coin, just like it'd be 1/2, wouldn't it?
But 1/2 means so you see, imagine you have no preference, no idea what's the probability with which the coin falls, heads or tails. So you create actually a distribution. You don't select a particular probability, you create a distribution. The probability is equally likely to be anything. So the how do you say, the distribution of probabilities you imagine to be between 0 and 1 uniformly. The probability is equally likely. In other words, if you were to play with this game and pick lots and lots of coins, right? So once you select a coin randomly, you toss it, you would observe that that the probability builds up pretty much anywhere.
Is it getting, as more tosses you get, as more normal it gets, as more like narrower?
Yes, so the more tosses we will narrow to the probability, but initially we have no preference. We have no reason to believe. The probability could be anything between 0 and 1, and each region is equally likely to us. And if this is not true, then it will be updated in a moment. You understand? Once we begin observing it, our default assumptions are updated. You see that? So we're going to create a random variable W, and W equals P. It has the beta distribution. Let's imagine it has any distribution. We say beta AB, but in particular, why would I imagine it has beta distribution? Because in particular, if I know nothing about it, I might imagine it has the uniform distribution. Imagining it has the beta distribution is even more general. But you can think of it as, you assume it has the uniform distribution. And of course, you would, and why did I select W? Because W is Wahrscheinlichkeit, and that's how you say probability in German. Okay, so what is my estimate? If I believe it has beta distribution with parameters A and B, its density function is 1 over beta of AB, P to the A minus 1 times 1 minus P to the B minus 1, okay? And let's see how the update will happen once I made the observation, right? So I need to calculate. So X is, let's say, the number of successes that we have here, okay? So I'll begin the experiment. I toss it n times, let's say, right? I toss the coin n times, and I observed I have k successes. K times out of the n did the coin land heads. How do I update my distribution? You follow what I'm doing here, guys? So I'm interested now in the new distribution. Giving this observation, my new distribution, I call it G of P. And that would be the density. It's called marginal density function, where it's the F, but given that X equal to K. Good. And here is, I think, the simplest way to do that is how do we estimate it? It means what? What's the probability? I want to know what is the probability that W is between P and P plus DP, given that I had K successes. That's essentially what I'm headed at, right? So you're trying to update the probability, right? So what's the probability, now that they made the observation, what's the probability that the coin, its coin's actual probability falls in a particular region? Good? In a particular region. So I select that particular region to be between P and P plus dP. And given that X is equal to K, that should be roughly the probability G of P times dP. Okay? Remember what is this meaning? Is the meaning of that is very simple, guys. The meaning is that if you select a very small region, so this is P and this is P plus dP, the curve G is supposed to satisfy this property is that roughly G of P times the width, so G of P times that's the height times the width, is supposed to give you the probability of in this local region. You understand what I'm saying, guys? In other words, what I think is this, is that I don't really even think of continuity. I think that my density curve is just the skyline produced by many thin rectangles. You see that? Many thin rectangles. So then the appropriate G should be telling me what's the probability, what's the likelihood that this is the actual probability of the coin. So for any region, for any base here, it's the likelihood that my coin has this actual probability of success. Good? You understand how this is that I'm thinking? I'm just entirely thinking in discrete terms. Right? So then let's do this calculation. GP dP is the probability that W is between P and P plus dP, given that X is equal to K, which is what? Which is the same as, I can recondition it. It's probability that X equal to K, given that W is between P and P plus dP. Yes? Times the probability that W is between P and P plus dP, the original probability, divided by the probability that X is equal to K. Good? Are you still following me, guys? You make me worried. So we condition on what is W. I want to calculate what is Px equal to K. Conditioning on W, that would be what? That would be simply W is, so it is this. Probability that X equal to K is the summation over all the P, where X is equal to K and W is in a particular region, times the probability W is in that particular region. Okay, now this part is simply the binomial formula. If W is in this particular region, the probability that X equals to K is n choose K, P to the K, 1 minus P to the power of n minus K, and FPDP is really the probability that W is in this particular region. That's the distribution of W. Are you still following me? That's good. You see, so I just use pretty much Bayesian statistics here, and so probability that X equals to K is simply what does it amount to? You see, I just add this thing up. You see, I factor the n choose K. What is this? It's just the integral from 0 to 1 of x to the k 1 minus x to the n minus k times f of x dx. And the probability that X is equal to K, given that W is between P and P plus dP, it's really very similar to the probability that X equal to K, given that W is equal to P, which is n choose K, P to the K, 1 minus P to the n minus K. So in essence, what you have is just work it through, right? This is just f of P times dP. This is, we calculate it over here, right? In other words, given that W is between P and P plus dP, I can approximate it as just as if W is P, what's the probability I get X equal to K, right? Essentially, W is P here. So that would be n choose K, P to the K, 1 minus P to the n minus K, times f of P dP, that is from here, and divided by this integral from 0 to 1, n choose k, x to the k, 1 minus x to the n minus k times f of x dx. Okay, which is just, this is just dividing by a scalar. So what is this GP? So if you take n choose k and you take this thing all together, it's just a constant times p to the k, 1 minus p to the n minus k, f of p. Okay, that's my G. And very simply, I can easily recognize what should be that k. Look at it. If I multiply the p's, I just get p to the a plus k minus 1, 1 minus p to the b plus n minus k minus 1. I just add the corresponding value. So what this means is that my distribution is now again a beta distribution. It's a beta distribution where I add k to the number of successes, and I add n minus k, the number of failures, to b. You understand? So starting from a beta distribution, you arrive at another beta distribution. That's what I'm trying to say. It's very important to understand this point. Okay, let me show you an example, and then I will re-explain it in case you need it. Good. So let's consider this example. Okay, so let's see if it makes it a bit easier. A coin is tossed 1,000 times. 550 tosses come up heads. Estimate the probability that the coin lands heads. Do you understand the question, guys? Right. So I know nothing about this coin. I do not know if it's a fair coin. If it's a fair coin, then there is nothing to estimate. It's always 1/2. It just, that's how it happened. But I do not know what sort of coin it is. Right? You understand how you model a non-fair coin? Truly, you just create a die with many faces, and you label some of those dies as heads and some others as tails. Right? So that's how you create an unfair coin. Because aside from that, every coin that you toss, if it has heads or tails, if you move it randomly, then it will be 1/2, obviously. If you flip it around randomly, good. So 550 tosses came up heads. What's the probability that the coin? What do we think the probability is that it lands heads? So we know nothing about the coin a priori, correct? And if we know nothing about the coin a priori, it's natural to select a uniform distribution for my first hypothesis. So my first hypothesis, it's just as likely to be 0 or near 0 as it is near 1, or anything in between. So I begin with beta 1,1. You understand why I begin with beta 1,1? And so I want to figure out this probability given that I had 550 successes. Okay, given that I had 550 successes, then the updated beta is 1 plus 550 and 1 plus 1,000 minus 550. And if I am not incorrect, it's 551, 451. That's my beta. And if you draw it, you get, using a software or not, you get this type of curve. Okay, you see what happens here? That's the curve. And what do you see? You see that you don't see exactly what's the probability, but you see the probability is, let's say, somewhere between 0.48 and maybe 0.6, right? So it's between 48% and maybe 60% or something like that, right? And everything else is essentially almost invisible. You see, so it's very likely to be well, sorry, the likelihood that it lands heads is the actual true probability is somewhere in the interval from 0.48, let's say, to 0.6, maybe, I don't know. You understand what I mean? And if you have more trials, it will narrow. It will, this curve will be narrowing and closing on the actual probability. But you just have an estimate. Okay. Okay, so here is an example that's, I'm not sure how interested you are, but I suppose it's still current, right? So in a city of 12 million inhabitants, it is wished to estimate the number of people that contracted a certain disease. Okay, what do? How do you figure out how many people contract a certain disease? Well, the best thing you can do is you take a random sample of the entire population and test them very thoroughly, rather than just go and test everybody from morning to night. Right? Just collect a random sample, and that will give you, and do it whatever how many times you need, and you would see how the disease progresses based on the beta distribution. Okay. So here is let's say what we have is we collected 100 subjects randomly. It's very important that they are randomly selected. If they're not randomly selected, this result is meaningless, right? So 100 subjects, diseased or not diseased, are randomly selected and very carefully tested for the illness, very carefully. And only 2 of those 100 individuals are found to be sick. What can we conclude about the prevalence of the disease in the general population? You understand, we don't know how common is this disease in the general population, but we're able to find it once tested, good, in any individual, once tested very carefully. So 100 subjects were selected and carefully tested. 2 of those subjects were found to have the disease. How prevalent is this disease in the population? So here is what you do. So initially, you have no knowledge of whether the disease is there or not. So you can always assume the default uniform distribution. You understand? If you assume any other beta distribution, it will change. It will be updated based on the results that you obtain. Okay? It will always be updated based on the results you obtain. So choose uniform distribution, and then add this information. What do we find? For this uniform distribution, we just need to add 2 people that are sick to A, and 98 people that are sick to B, and we get the beta distribution of 3 and 99. And that is the distribution here. You see, it has this tail coming to the right. Okay. You see what happens here, right? So you cannot, of course, estimate it exactly, but based on that, you see that the actual probability of being successful or not is, this I imagine is somewhere between 0.01 all the way to maybe 0.1. So based on this sample, I can be extremely confident that the actual prevalence of the disease is anywhere between 1% and 10% of the population. Okay, so between 1% and 10% of the population is sick. If I have a bigger sample, this will be more precise. I can narrow down to the actual prevalence of the disease in the population. Do you follow how the beta distribution works, guys? All you have to do is understand why that will work. Do you have questions?
So in this case, do we mark the first, first 3 individuals as the sick or the infected people?
It's just the way the 3 is the updated beta distribution. See, so what we proved, and we can prove that again if you missed it. We proved that if you begin with the data distribution and then you conduct independent trials, right? And you observe how many successes and how many failures you have for those trials. What you do is you have the alpha parameter of the distribution. You add the number of successes to the alpha parameter, and you add or maybe to the A parameter. You add the number of successes to the B parameter. You add the number of failures. Make sense?
So the B parameter is the failure. The A parameter is the success.
Yes. Yes. Kind of, right? So so you just add those parameters and that will update the beta distribution. Okay.
And
so what you do is you begin with what was your prior assumption, right? It's always nice to assume. So how do you update your assumption? So you always update them based on observation. You understand? So you begin with no observation. So you begin with uniform. If no observation, you have no reason to believe that probability is anywhere in particular, right? You don't have any reason to believe it's 1/2 or it's close to 0 or it's close to 1. If you have no observation, you have no reason to prefer any interval for probability over any other interval. So it's always reasonable to begin with beta or with the uniform distribution. Beta 1/1, because the way it's set up is that it's always A -1 over the X and B -1. So it's it would be, I would have said the same, but it's just the way it's set up is yes. It's just the way they, for convenience, decided to set it up. Different conventions, I suppose, exist, right? So just the way we set it up is A minus 1, B minus 1, right? Yes, can you see me, guys? I got cut off. What it is, what is this beta, right? So there is essentially, forget about the coefficient, right? So what you have is you have x to the power of A minus 1, 1 minus x to the power of B minus 1. That's how you write it, right? And this is integrated from 0 to 1. And because the integral from 0 to 1 will not in general equal to 1, you need to multiply it by a constant, right? That constant is called, it's called 1 over beta AB. That's how they call it, okay? So it's a matter of names, obviously, right? So notice that beta of, so how do I make it uniform? I want A to be equal to 1 and B equal to 1, based on this notation, of course, right? You can create, just like that's the conventional notation, at least as I'm familiar with, right? So of course you could have said beta 0 0, but then you mean then that you are doing x to the A 1 minus x to the B. That will, in terms of integral, in terms of everything, it will give you the same thing, but they prefer to write it as A minus 1 B minus 1. Good. And the idea, and that's what you have to really just understand. The idea is, if you start with one such distribution and you update it with number of successes and numbers of failures, you will not escape the distribution. You will just create a new beta distribution, right? It just reshapes the graph. So once you reshape the graph, you have a new distribution. Now you have more observations, you continue reshaping the graph all the time, right? You could have started with all the observations together, add them up, and you will get this graph. Or you can start with first observation, upgrade, then add the next observation, upgrade. It will create the same distribution at the end. You understand? So for example, I conduct one study and out of 100, I found 2 individuals that are sick. And then I do it again and I find 5 individuals that are sick. I can do it as first I have 200 people and 5 plus 2, sorry. Or I can update one distribution and then I have no longer uniform and update it again with the 100. You understand? It will produce the same exact result, same beta. All right, so here is, so you see here I said it's the probability that it's between 1% and 10% is about 91% likely. But you can just kind of look at the distribution and see where it's very, very cut off, and you kind of get a sense of what's the actual probability. And if you have many samples, a big sample, then this would be a very narrow hill. So the probability will be focused around only some values. Good. Let me release the cat. It was actually what you call a rakirovka or cat exchange. So it was the gray cat, and now it's this thing in here. So I'm going to toss this out as well. All right, are we ready, guys? A new medicine against migraine is going through trials, and participants are admitted to the study. What is the probability that X, the number of participants whom the medicine helps, is equal to K? Okay. We're trying to figure out, without knowledge about the situation, about what the actual effectiveness of this medicine. We assume, of course, we don't have any preference, right? We don't know anything about this medicine. It might help very much. It might not help at all. Make sense? Ready? So how do I solve A? All I do is this. By default, I have no knowledge of the effectiveness of this medicine, so I assume it's uniform. And of course, most likely I'm wrong. But that's a good default assumption because there's no preference. You see, why uniform is natural is you're balanced. You don't have preference to say that it's a very good medicine or very bad medicine. You are completely indifferent. You believe randomly it's equally likely to be anything, right? That shows no bias at all. You see that, guys? Uniformity means no bias at all. And then I want to know what is the likelihood of k successes. So that will be the integral from 0 to 1, n choose k, p to the k, 1 minus p to the n minus k. Because what do? I condition based on what is the probability of success, right? And this dp thing, right? dp is my conditioning, right? So it's this probability dp, another p dp, right? So that, and the integral is just the sum of those probabilities. Let me just emphasize that again, how I think, so that you see the situation. So here is what I imagine, right? So when I see that my probability is continuous ranging, I imagine, in fact, that it's discrete ranging. So I imagine it's like this. And in general, if this is P, this region is dP, right? So basically the probability that X is equal to K, given that P is equal to this P, is simply n choose K, P to the K, 1 minus P to the n minus K. You agree? But I'm interested in the probability that X is equal to, I'm interested in the probability that X is equal to K, which is this probability multiplied by the probability that P is equal to P. But because I made it discrete, the probability, basically this entire region is collapsed to P. This entire region is collapsed to whatever this point is, right? So what do I have here? I have, in essence, the summation. This integral is just a summation sign. So I sum up over all the P's that are gathered here from 0 to 1. And dP is that probability. You follow? So I did it without using the Riemann sum, right? I didn't use the sigma notation. I just did it, so to speak, already abstractly, right? So that's what this integral is meaning. It's just add up all those segments, dP. And dP is the probability that p equals to this p. No, I mean, because I imagine that this entire interval is p. Okay? Okay, what do we have there? Exactly. And the general would be 1 over exactly Naomi and exactly Chabeli, right? So this entire thing is simply equal to what? It's simply equal to 1 over n plus 1. Beautifully. I hope you understand the reasoning for that. Good. So instead of doing this integral, it's much simpler because I just realized what it means. Is that it means that based on that example with the n plus 1 balls, it means that there are k balls below the special n plus 1 ball, and the probability is simply 1 over n plus 1. Good. So we have n participants. The probability that and notice it's the same, right? The probability that k will be helped by the medicine or healed. I'm not sure what do they say. So it will help them, and so it would be 1 over n plus 1. Now, and now let's say this, given that the participants in the study are positively affected, what is the probability that the true potency P of the drug is greater or equal to 1/2? That it's more, so all the participants, I had N people that I sampled, all of them were helped by the medicine. What's the probability that the actual effectiveness of the drug is bigger than 1/2? In other words, it's more likely, it's likely to work on more than half the population. All right, let's do it together. So what do we have here, right? So if all of them were affected, it means that 1 minus P is to the power of 0, right? Everything is a success. So it's the integral of, so it's the integral of P to the N. We know that this integral is 1 over N plus 1. Agree? Because all of them, I mean, this just means X is equal to N. Right, so the probability that without knowing anything about it, the probability that X is equal to N is 1 over N plus 1. They're all the same, right? It's equally likely to help 0, 1, 2, 3 without any further knowledge, right? So because of that, I know that the beta distribution N and 1 is equal to 1 over N plus 1, right? Because what happens here is, yeah, that's just beta. That means just beta where, did I say correctly, right? It is, no, I mean, something is off here, right? This should be a beta of N plus 1. So I made a mistake here, right? It's beta N plus 1, correct? Because over the probability P, it should be N minus 1, right? So that is, I made a mistake here, I think. It's N plus 1. Good? And that would equal to 1 over N plus 1. So now what's the probability that P is bigger than 1/2? That simply is, it's just what I have to do is I have to multiply this by 1 over beta, right? So I have this distribution, I have to integrate 1 over beta, P to the N, 1 minus P to the 0. I'm just actually evaluating the beta distribution. You see, so the function after I receive N of them and successes, it means that I just have, this is what happens if I have N successes. That's how the beta distribution is updated. I was dealing with beta of 1, 1, and now it's beta of 1 plus N, 1 plus 0, right? So what am I evaluating? The probability that we have the effectiveness is more than 1/2 is from 1/2 to 1, and I integrate 1 over this beta. Times P to this number minus 1, so N, and 1 minus P to the power of 1 minus 1, which is just this, dp, right? And I know this number. I know this number here. Right? This number is simply equal to n plus 1. Do you agree? That's what we calculated over there. So wonderful. So simply what happens here is that it's n plus 1 times p to the n, and its integral is just p to the n plus 1 evaluated from 1 to 1/2. So it's 1 minus 1/2 to the n plus 1. That's the probability. It's more effective. Well, it's effective to more than one half of the population. Good. And that concludes the lecture on beta distributions. I hope you enjoyed it, and I hope you realize that you know that that's what they do with all the tests, or at least what they did with all the tests, is really very stupid, right? The lines, whatnot. Well, have a good one.
Wait, Professor, why do we use n plus 1, beta n plus 1, 1?
Why beta n plus 1? Well, it's just the way the way it's defined is if I have beta of a b, that means what? That means the integral from 0 to 1 of x to the power of a minus 1 minus x to the power of b minus 1 dx, right?
Yeah.
And this is the very important thing that you should kind of derive by yourself, and then if you don't understand it, ask me questions about. Do you see that my observations affect this this beta? So if this was my original distribution and I observed let's say k successes and n minus k failures, then I simply have beta of a plus k and b plus n minus k. That's my new beta. That's the update. So initially, I assumed nothing about the effectiveness of the drug, so I had this beta. Then I observed I have n successes, so it was 1 plus n, and 0 failures. So that's the update.
Oh, okay, I see it now.
Okay, but so you have to understand how the update is happening. You see, guys, that's a very important idea, and see if you agree with it. Okay, and
so do we just usually assume that like A is the success and B is the failure? That just makes it easier.
yes, you can assume that A is the success and B is the failure.
Okay.
Right? If that so, A is the parameter corresponding to success. That's where you add the success, right? But you have to be careful, because notice what it assumes. So it's always it's success minus 1 truly, and this is failure minus 1, because if you have failure, if you have b equal to 1, it means you had 0 failures based on this notation. Okay.
Yeah.
Yeah.
So will you be continuing your lectures just at class time next
Good,
Monday?
good. So here is what I propose to do, and again, don't feel bullied by me to anything. I just kind of feel that I failed you, right? Well, I'm not literally I haven't yet literally failed you, right? Although the first exam was not terribly good, and I do notice what you call it, some extra effort by either group or copying from somebody, right? So yes, but most of it was actually copying, and also not good copying, right? Because I see the same solution and it's entirely wrong. I propose that we go over those questions on well, possibly on Monday or before. I still have to deal with my calculus students. They're kind of washed down, so to speak. So I try to make them survive for Tuesday, because that's when their exam is. But I propose that we do meet on the regular time on Monday. Since your final is, I'll just make it a take home. I hope you are enjoying and another thing is I will need your final sooner than I hoped, because on the 23rd I must post all your grades. So I'm going to send you the final. I'm going to write the final, send you the final, and right? And you deliver the second exam by, what did I say? By
I think in your email you say 16th.
Yeah, so try to do it by the 16th so I can grade it. My God, how do I hate grading probability exams? You cannot imagine, right? It just,
This is what you need PhD students for, to do it for you.
oh yeah, exactly. I don't know what I need for, right? What I need is, well, so you see, this is the double-edged sword. I think you fail as my darlings. You tried, but poorly. But then you succeed. I think you cheaters. Anyhow, whatever, right?
Well, you can give your favorite students like A's. You can always give your favorite student A's.
Yes. Well, I mean, all of you are. If I saw your face, you're probably my favorite.
But Professor, it's hard to copy anything because you creating your problems. It's not on Chegg, so.
Well, yes. Okay. So I see. You were trying to find them on Chegg. Well, it's not.
It's like I know that like it will be impossible, but when I took calculus 2, it was the class was at 7:10 a.m. and my professor was always late. And then sometimes at 6:30 he says, "Oh, I don't feel well," and then he canceled a bunch of classes. So in Calc 2, we had
He was Professor Chess?
No.
Okay.
So, and then in Calc 2, we had take-home exam number 2, which was like the best thing for us to have.
I'm sure you're glad. So,
no, but what I wanted to say is that a bunch of people copied the wrong number from Chegg. And my professor, he got so mad. He said, even if you copy, it's okay, but copying wrong is so disrespectful to me. So.
Well, I don't know, disrespect. Yes, I mean, I do get upset, but I try not to get it too much to my heart, right? I hope that, you see how I'm going to verify it. I think the grade kind of, it's already kind of everything inflated, money is inflating. I'm surprised it's still not, prices are not twice as much. So why not grade? So, but what I'm gonna try is you're gonna stay with me, of course, right? We're gonna do even in the winter break. We will meet a little bit. Maybe we'll see if you want to meet, right? We'll see how pure is your heart, and we continue doing very hard, brutal probability problems together, right? Discuss. What do you think? Maybe I'll post a nice textbook, right? And we can work through the problems there and compare solutions.
I mean, you said we're gonna meet with Probability Monday, Wednesday, forever now.
Yes, I mean, if I had no other activity, I would probably keep you forever, right? It's a perpetual probability meeting, right?
Wait, is anyone statistics major?
Statistics major? Oh yes, that was me.
So, but what's the next class? Is 312? Are you teaching 312 or?
No, I'm not. I'm not an expert in probability by no means. Just I know a little bit here and there. Try to know more, right? So yes, but you're good. I am statistic. Yes, I want to go into the 7th layer, right? Statistics major. That's me.
How hard is 312 if this is 311?
Well, that depends on what you teach. The questions are hard. Some of them, right? Some of them are easy. Some of them are hard. So it's not like I think some of you are very good. I'm very impressed with how you are processing the information, right? So I feel almost like I need to find or create really hard problems, right? So that you are.
No.
Yeah, so that people would meet you, like, what happened to you? How are you so good in probability? Right?
No, we don't find them online. But also, some of your problems from the last exam, they could trigger people.
Of course.
Like the 6B, 6 about girls, assigning non-gender, what?
Well, I try to entertain people, whatnot, right? Usually I'm like a minesweeper, right? So my first statement, I just have to know what a person finds annoying, and that will be my first statement. How do you do, right? Right?
Yeah, some people might be.
Yeah, well, yes.
Not in our class, but if you would, I don't know.
Probability students, how can you be upset about anything truly? Right? You just, for you, it's just like beta, alpha. I mean, you don't have any feelings anymore. So it's, right?
It's all numb.
It's all numb, right? So you cannot be too upset, right? It's like a swimming in cold water.
Yeah, right? But it's interesting how different majors people work, like think differently. Like when I go to my psychology major class, like everybody gets upset with little things.
Well, yes, that's why they went to psychology. They were hoping to cure themselves, right? they go to psychoanalysis, right? Whatnot.
Yeah, this is actually what I want to do for a living.
What's psychoanalysis?
Mm-hmm.
Well, actually, people come to me to discuss problems with me, right? All sorts of like, hello, right? I want to die. And they always come to me for that.
And you're like, here's the probability of that.
No,
People, when they get very sick or very sad, they always remember me. I guess the angel of death is at my shoulder, right? So they always come.
Professor,
Sorry?
Professor, what did you say in the beginning of the class? I couldn't get into the room.
The beginning of the class? What did I say? I said that I'm going to send you the exams. Okay. Don't be too disheartened, right? I did not grade. Well, I mean, I graded based on how I think. The exam is not how I think of you, right? Most likely you will get a better grade, right, than what's on the exam. But what I want you to do before kind of any sort of barterings, we don't need to barter, right? We're all just there for knowledge, so to speak, to make eternity seem shorter, right? So you just work on exam 2, and I will write the final, and we'll see what I'll be motivated by, right? So you don't want a very difficult final, right? You want a kind of an easy Christmas, nice, happy final. I don't know. I mean, when I find a nice problem, I think, my God, that's such a nice problem, right? So.
Yeah, is this final going to be your Christmas present to us?
Yeah. Yes.
Wait, you write the problems yourself, right?
Some of them I write myself. Some of them I just find the problem, right? Because I mean, how much do I think about them? I find a problem, I might word it differently, but essentially the mathematics of it is simple, right? Some of them I write myself. Some of them, you can tell some of them that I write myself, of course, right?
Yes.
Exactly. So
the
ones that are kind of more, normal, that means most likely I didn't write them.
What? What did you
if it seems like a normal kind of normal problem, then it's probably not me, right? Who wrote it, right? My problems are always,
You like to introduce characters, I've noticed.
Characters? What characters?
Like, I don't know, one of the problems is just that, like, whoever, like, I forgot the name, but it's like, whatever, it doesn't like if you get the probability wrong or whatever.
Well, actually, in some exams, I mean, the way I came up with the program, somebody stopped talking to me, right? I got offended, stopped talking to me. I think, that's a probability problem, right? Exactly. By what they got offended, I just immediately made it a problem for the class. Yeah. It's a bad thing, people get offended too much here. We need to undo the offendedness, right? The firing of your neurons. You have to be less sensitive.
So, Professor, how often would you say something and people get offended and you think, oh, I shouldn't have said that?
Well, rarely, right? I mean, only strategically, right? What do you think strategically what can happen, right? But aside from that...
I mean, if you're in Russia, that dude's just going to punch that glass door and walk out of the train.
Ah, yes, you've seen it, right?
Yeah, that
With the calculus class, I was playing what, when, where. There are some people that actually are getting better at it. Right? Yeah. So yes, you don't mind coming on Monday, do you? Or you do mind?
No.
Right? If not, I'll send an email. I'll schedule this class, and we can kind of continue learn the material, and we'll see what.
Professor, I need the help.
I have a review session, so I might be a little late, but I will.
Okay,
I will be there.
That's nice. I would be happy to see you. And yeah.
Well, the Monday is like what, different day schedule or something? No.
It's just final schedule, so it's whatever final you have.
It's reading day. I will probably be dealing with my calculus students to help them survive the Tuesday exam. Right? I was not able to cover everything, just like with this class, but for them it's worse.
Your calc exam wasn't that bad.
But it's not mine. It's going to be someone else's.
Oh yeah, it's the department's, isn't it?
The department, right?
Yeah, so, but it wasn't that bad.
Yeah.
But the final, does department check how you graded the final?
The department has fallen asleep. They decided that they trust me, right? So mostly the department doesn't bother me, but who knows, right? Who knows? Who knows? Don't get any ideas.
Mm-hmm. They might sample some and check.
Yeah, so we'll see, right? I'm not at all an expert in probability. That's why I'm like teaching it. It's like, I see what you do. I learn from you still, right? Calculus is boring. I don't learn anything mostly, right? But from you, I learn. You have sometimes very interesting solutions, and also it's kind of it's just I find probability very interesting. Is that I think you see mostly in mathematics people answer a question and they don't care what the solution is, if it's correct or not correct, so they can easily make a mistake. But what if you make a mistake and you really care that your mistake is correct? It's like the mistake is life or death. It's like, they will get offended, they will get angry, they will defend their mistake to the death, right? And yes, and
Professor, what were you majoring in?
me, psychology. Psychology and German.
Social psychology. Gender is a construct, right?
I don't know.
You went into psychology and offended everyone.
Me? Yes. I majored in psychology, philosophy, German, and math, right? Mostly psychology, I thought. I transitioned into mathematics from it. Mm-hmm. Yeah.
So what, mathematics and German philosophy?
Well, German literature and just German, just philosophy, but German literature. You know this, what I do, right? As I sit here with calculus students, they bore me in the middle. I just turn on the microphone and I help the German policeman, speak Russian. If you want, I can play for you his recording. You would recognize this thing, right? It's actually pretty good.
So, do you have a hard time living here after Germany because it's a mess compared to Germany?
No, Germany is a terrible place to live. What do you mean? You think there it's great? No, they obey.
Oh, they're like so structured and they're like robots. I hated being there. I wouldn't ever want to move there.
They're yes, exactly. They're like robots.
I used to spend some time.
Sorry?
I used to spend some time in Bamberg, and I was just dying from boredom there. But the food is good, so. German
food? I don't know. It's almost like a challenge, In Germany, it's like you speak with aliens, right? And you think, how are you able to? I was inaugurated already some of them inaugurated me to their friend. But this German police. So he's a policeman, actually. The other day got jumped by 5 people, he and his partner. So, right. I wanted him to, but it was too dangerous for him. We actually wanted to, I really hoped that he would make the video so that I will scare my calculus students, right? About being investigated by German police. But he said he can be in a lot of trouble if he does it. I would have done it, I don't know.
I mean, he has your consent.
Have you seen the video? I can show you the video he sent me from the police department. Anyhow, I hope I'm not bothering or holding you guys. If you have to go, you have to go. But if you want, I'll show you what is the meaning of cheating for Russians. I can show you a short video, right? So it's when people cheat, I have a mixed feeling about it always, right? And here is the reason for it.
How you cheat, right?
Huh?
Depends how you cheat, right?
Well, I mean, the codex of a Russian student is that you help your fellow classmates cheat, but the codex of a teacher is you catch them, right, or whatever it is. So it's and of course you never rat on your fellow inmates, right, or classmates.
Niches got stitches.
Exactly.
Right. When you told the story from your calculus class, how those girls told another girls, I was like, that would never happen to Russia, right?
Well, I don't know, but